powerful level 4, G4, geomagnetic storm is currently impacting Earth, triggered by a significant coronal mass ejection, CME, from the Sun on May 30th, 2025. This event is causing auroras to be visible much farther south than usual, with sightings reported as far south as Alabama and Northern California. The storm is expected to persist through June 4th, potentially disrupting satellite communications, GPS systems, and power grids. In this video, we'll delve into the causes, current impacts, and potential consequences of this severe solar event. What is a level 4 solar storm? A level 4, G4, solar storm is not just a typical burst of solar energy. It's a severe geomagnetic event that shakes Earth's magnetic shield. These storms can disturb radio communication, cause unexpected power grid malfunctions, and even make airplanes reroute across polar routes. When a G4 event occurs, space weather centers worldwide issue alerts due to the heightened risks. What we're seeing right now is a rare and powerful instance of such an event, brewing from deep within the Sun's fiery activity. When we say level 4, we're referring to the NOAA space weather scale, where G4 means KP index 8 or higher. This magnetic index is like a Richter scale for geomagnetic storms. The higher it climbs, the more chaotic the magnetic field becomes. At KP8, Earth's magnetic shield starts to ripple and shake, allowing charged particles from the Sun to push deeper into our atmosphere. These geomagnetic storms affect both space and Earth-based technologies. Satellites may lose orientation, GPS can become inaccurate, and electric grids may experience voltage irregularities. For individuals using ham radio or flying over polar routes, disruptions become noticeable, sometimes dangerous. Even oil pipelines can experience surging currents that wear down infrastructure faster than normal. On the ground, the most visible impact of a G4 storm is the aurora, or the northern and southern lights. During severe geomagnetic activity, these beautiful waves of green, red, and purple light can stretch far beyond their usual regions. In this current storm, people in Colorado, Virginia, and even Northern California have reported aurora sightings. That means Earth's magnetic field is experiencing serious compression. The danger of a level 4 storm isn't in one big blast, it's in the duration and layering. As the magnetosphere weakens under constant bombardment, even moderate bursts become damaging. Right now, NOAA reports continued storm activity through June 4th, meaning we're facing not just a flash storm, but a sustained one, and that can change atmospheric dynamics rapidly. What makes this event more concerning is how early it arrives in the solar cycle. We expected solar maximum to peak in late 2025 or early 2026, but this intensity in mid-2025 indicates we might be hitting stronger peaks sooner than expected. This raises questions. Is the Sun's activity accelerating unnaturally? Or is this a normal but misunderstood pattern? Scientists are watching closely. The coronal mass ejection behind the storm. On May 30th, 2025, a massive coronal mass ejection, CME, blasted from the Sun's surface, specifically from sunspot AR3697. It wasn't a typical solar flare. This was a halo CME, meaning it was aimed straight at Earth. NASA's SOHO and Stereo spacecraft confirmed its Earthbound trajectory within hours. The speed of this CME was measured at over 1,900 km/s, placing it among the fastest of the solar cycle. When such a CME hits Earth's magnetic field, it causes a sudden compression known as a magnetospheric shock. Think of it like a balloon being squeezed hard. Pressure builds instantly, and particles flood into the atmosphere. That's what triggered the current level 4 storm. This particular CME wasn't alone. It was followed by high-speed solar wind, amplifying the effect like wind adding fuel to fire. Sunspot AR3697 itself is a monster, large enough to fit 10 Earths across. This region has already produced multiple M-class and X-class flares in the past week, making it one of the most active regions of the current cycle. Its magnetic field is highly complex, with twisted magnetic loops indicating high instability. Scientists use a technique called coronography to track CMEs. In this case, coronagraph data showed a dense plasma shell wrapped around the ejection, a signal that it could carry significant momentum. Combined with the high-speed stream, the CME created a perfect storm condition for Earth. It's rare to see both high density and high speed in one event, but this was it. This event is being compared to the infamous Halloween storms of 2003, which knocked out satellites and caused radio blackouts. While current infrastructure is more resilient, we are more dependent than ever on GPS, aviation systems, and satellites. That makes this storm more economically risky, even if it's not the most powerful in history. The next question is, will there be more? Sunspot AR3697 is still facing Earth, and it continues to grow. The possibility of another CME in the next 72 hours remains high. This means our planet may not be done yet. The June Sector 4 storm could become a multi-wave event, stretching longer and growing in intensity. All eyes are now on solar monitors. How Earth's magnetic field reacts under impact. Imagine a protective bubble surrounding Earth, invisible yet critical. That's our magnetosphere. When a CME hits, it's like a punch to this bubble. But this time, the punch was harder than usual. As the shock front slammed into Earth on June 2nd, satellites registered rapid magnetic shifts within minutes. It wasn't a gentle tap. It was a magnetic quake. These solar winds compress the day side of our magnetosphere and stretch the night side like a rubber band. That stretching creates a magnetotail, and when it snaps, it fires energy back toward Earth. This magnetic recoil is what sparks powerful auroras and atmospheric currents. On June 2nd, that tail was pushed deeper than scientists predicted, signaling a more intense internal shock. But here's the hook. When the field distorts, navigation systems start drifting. GPS becomes unstable. Compass directions can subtly shift. In some regions, like Alaska and Norway, measurements deviated by over 5 degrees. If this continues, even missile defense systems can misalign. And nobody's talking about that on the news. This impact also creates magnetohydrodynamic waves, invisible ripples in Earth's magnetic fabric. These waves can enter ground-based power lines and cause surging currents in transformers. That's what happened in Quebec 1989, total blackout in 92 seconds. Engineers are watching now because the readings from June 2nd are eerily similar. To keep this shield stable, Earth's ionosphere tries to absorb the energy. But when the storm's too strong, like now, it overloads. The result? Ionospheric heating, radio blackouts, high-frequency disruption. Pilots flying over the poles right now are being rerouted, not because of weather, but because space is screaming. This isn't just science, it's survival tech. The magnetic field is our only true defense against space radiation. The more it's shaken, the more vulnerable we become. And right now, that shaking hasn't stopped. Scientists are now calling this storm one of the most complex field distortions of the solar cycle. Why proton storms are dangerous for our atmosphere. While everyone focuses on the solar storm's visuals, few talk about the proton storm hidden behind it. Level 2 proton events are fast-moving particle barrages that bombard the upper atmosphere. These aren't slow, glowing waves like CMEs. These are invisible bullets. They reach Earth in minutes and hit hard. On June 2nd, satellite sensors detected a sharp spike in proton flux. These particles, traveling near light speed, slammed into Earth's poles, overwhelming the ionosphere. Radio blackout zones appeared almost instantly over Canada, Greenland, and parts of Russia. Imagine turning the dial on a radio and hearing nothing but static. These storms are especially dangerous for astronauts aboard the ISS. Normally protected by Earth's magnetic field, high-energy protons during solar events can penetrate thin shielding. During this storm, astronauts were ordered into shielded safe zones, the same alert level used in previous X-class events. Even aircraft flying above 35,000 feet at polar altitudes are at risk. Radiation levels can spike to 100x normal. Pilots and crew could receive radiation doses equal to multiple chest X-rays within hours. Many airlines are now grounding or rerouting flights until the storm passes. You might think this affects only the skies, but protons hitting the upper atmosphere trigger ozone depletion. That means temporary vulnerability to UV rays in certain latitudes. In 2005, a similar event caused a 60% drop in ozone levels over the poles. The June 2025 event may be repeating that pattern. Proton storms don't make the news, but they shape the skies. They cause silent disruptions in our planet's upper shield and introduce long-term ripple effects. What we're seeing now is the kind of event that changes how the atmosphere behaves in the weeks to follow. And no, this isn't over yet. This solar cycle is stronger than we expected. The current solar cycle, officially known as Solar Cycle 25, is proving far more powerful than scientists predicted. While initial projections showed a weaker phase, the Sun has already unleashed intense activity months ahead of schedule. What we're witnessing is not normal variation. It's a growing solar force rewriting the forecasts. Sunspots, which are the main engines of solar eruptions, are appearing in higher numbers and larger sizes than expected. Sunspot AR3697 alone has produced multiple X-class flares, a rarity for this phase. The increasing magnetic complexity of these regions suggests a more turbulent peak ahead, possibly by late 2025. This solar cycle is also producing more overlapping events, where solar flares are followed immediately by CMEs and proton storms. The combination of speed, density, and frequency is something we usually observe closer to solar maximum, not midway. It shows we may be heading into an unexpected spike in solar aggression. Experts are now considering revising their models altogether. The Sun seems to be entering a more chaotic phase, accelerating toward peak energy. If the current trend continues, we could see multiple level 4 or even level 5 storms within the next few months, making this one of the strongest cycles in decades. What Sunspot AR3697 tells us about solar behavior. Sunspot AR3697 has become a major focus for space weather scientists. This enormous region is magnetically unstable and carries the potential for more large eruptions. Its structure indicates a beta-gamma-delta magnetic classification, one of the most dangerous, capable of generating powerful and frequent X-class flares. The way this sunspot evolved is unusual. Within just 48 hours, it grew exponentially, with multiple cores twisting into one another. This level of complexity makes the magnetic field unstable and prone to sudden explosive events. Scientists refer to this as magnetic shearing, a precursor to violent space weather. AR3697 has already caused several Earth-directed CMEs and is expected to remain visible for the next few days. As it continues rotating across the Sun's Earth-facing side, the risk of another direct impact increases. Every hour it stays active is another hour Earth remains vulnerable to space disruption. This sunspot also reflects a larger pattern. We're now entering a phase where sunspots are becoming more unpredictable, faster forming, longer lasting, and more dangerous. If this is a sign of what the Sun has planned for 2025-2026, then this may only be the beginning of a very volatile season. How auroras reveal the storm's true power. Auroras are not just breathtaking natural lights, they're living proof of Earth's magnetic field fighting back. When a solar storm reaches us, these colourful displays become brighter, wider, and more intense. And during the June 2-4 event, auroras were seen as far south as Oklahoma and southern France, an extremely rare occurrence. The colours of auroras also reveal their intensity. Green lights are common, but when storms grow stronger, deep reds and violets appear. These shades mean the storm energy has penetrated deeper into the atmosphere, creating more energetic particle collisions. The current auroras show just that. Another sign of the storm's power is duration. These auroras haven't faded in a few hours. They've been glowing for multiple nights in a row. That means the solar wind stream is strong, continuous, and not letting up. A serious red flag for ongoing geomagnetic stress. In ancient cultures, auroras were seen as omens. And maybe they were right. Because what we're seeing in the skies isn't just beauty. It's the visible effect of an invisible war between solar energy and Earth's only line of defense, the magnetosphere. Satellites are at risk. Here's what may happen. The first casualties of solar storms are usually satellites. These delicate machines orbit Earth in a region directly exposed to incoming solar radiation. And right now, solar particles are colliding with satellite shielding, heating them and disrupting onboard electronics. Any glitch in orientation or data relay can cascade into real-world outages. Solar storms also inflate the atmosphere, increasing drag on low-orbiting satellites. When this happens, satellites lose altitude and start falling toward Earth unless corrective thrust is used. This already happened during a 2022 storm that took out 40 Starlink units. And the current storm is even more intense. Communication satellites are particularly vulnerable. Disturbed geomagnetic fields can cause signal distortions or even complete blackouts, especially in higher latitude regions. This affects everything from television signals to aircraft navigation systems, raising serious safety and operational concerns worldwide. To avoid catastrophic failure, many satellite operators have already begun switching devices to safe mode, limiting operations, and monitoring for radiation spikes. As long as the storm continues, Earth's satellite infrastructure remains in a delicate balance, and one strong shock could cause major disruption. Can these storms affect power grids on Earth? Solar storms don't just stay up in space. Their effects reach deep into our lives. When strong magnetic fields from a CME hit Earth, they generate powerful currents in the ground called geomagnetically induced currents, GICs. These invisible electric surges flow through power lines, transformers, and substations, often damaging critical infrastructure. In 1989, a level 5 storm caused a complete blackout in Quebec, Canada. Within 90 seconds, the power grid collapsed. What's concerning now is that Earth is once again experiencing high GICs during this June 2025 storm, with readings spiking in North America and parts of Europe. The grid today is more connected, but also more fragile. Modern power systems rely heavily on automation and real-time data. When GICs distort signals or trip sensors, entire sections of a grid can shut down to protect themselves. But these shutdowns can cascade, especially if transformers overheat or relay stations fail to sync. Engineers around the world are on high alert. Experts now use magnetometer arrays to monitor ground currents in real time. With the current storm still active, they are closely watching for red zones, areas where Earth's crust is conducting too much current. If left unmanaged, the next big solar hit could fry more than just wires. It could bring entire cities to a halt. air travel and radio communication disruptions. Explained. Airlines across the globe have been on high alert since June 2nd. That's because solar storms severely disrupt high-frequency radio, HF, the backbone of long-distance aviation communication. When radiation hits the upper atmosphere, it absorbs and scatters these radio waves, silencing them mid-flight. Pilots flying over polar routes, such as New York to Shanghai or London to Tokyo, are the most vulnerable. These routes are closer to the magnetic poles, where solar particles are funneled more directly. During this storm, many airlines were forced to reroute flights, burning more fuel and delaying landings. It's not just commercial flights. Emergency frequencies, search and rescue communications, and some military systems still rely on HF radio. A blackout during critical operations could mean lost contact, missed distress calls, or navigation failure. In some cases, flights switch to satellite backup, but even satellites are struggling during this storm. To manage this, agencies use models like DRAP, D-region absorption predictions, to track where radio blackouts are happening. During the June 2-4 event, red zones covered large parts of the Arctic, Canada, and Scandinavia. Until the storm eases, flight paths remain under daily re-evaluation. NASA and NOAA emergency space weather alerts, June 2-4. Within hours of the CME detection on May 30th, NOAA issued a G4 watch alert for June 2-4. This type of alert means a severe geomagnetic storm is likely. As plasma reached Earth, the Space Weather Prediction Center upgraded this to a G4 warning, notifying aviation, energy, and communication sectors worldwide. NASA satellites like DSCOVAR and ACE observed solar wind speeds crossing 800 km/s, along with dense particle clouds. Their sensors also detected rapid shifts in the interplanetary magnetic field, one of the key signs a storm will strongly couple with Earth's magnetosphere. This is when emergency protocols go live. These alerts are sent out to grid operators, pilots, satellite companies, and even military departments. It's a global coordination effort. From North America to Europe, systems were bracing for potential voltage surges, loss of satellite orientation, and radio signal fading. These alerts help minimize the damage. People often think of NASA as space exploration only, but during solar events, it becomes Earth's first line of warning. Their early detection systems give us just enough time to prepare. Without them, we'd be flying blind into electromagnetic chaos. Could solar storms trigger earthquakes or volcanoes? It's a question that sparks debate. Can geomagnetic storms cause earthquakes or volcanic eruptions? While mainstream science hasn't confirmed a direct link, multiple studies suggest that intense solar activity can cause tiny shifts in tectonic stress, especially near fault lines already under pressure. When Earth's magnetic field is disturbed, ionized particles interact with the crust, especially in mineral-rich zones. Some researchers believe this electromagnetic agitation could act as a trigger, not a cause, but a final push. Interestingly, several moderate quakes have coincided with past solar storms, including events in Chile, Japan, and Indonesia. Volcanoes, too, have shown patterns. Historical data reveals a higher frequency of eruptions during peaks in the solar cycle. This includes famous incidents like Mount Pinatubo in 1991, which occurred just months after a series of geomagnetic storms. Coincidence? Possibly, but it continues to be studied. Right now, earthquake-prone zones like the Pacific Ring of Fire are under watch. Scientists aren't sounding alarms, but they're watching closely. Because while solar storms dominate the sky, their whispers may reach far deeper, into the Earth itself. The truth about CME speed and arrival time. When a coronal mass ejection, CME, blasts from the Sun, its speed determines not just when it will arrive, but how much damage it might cause. Most CMEs travel at 400 to 800 km/s. But the June 2025 CME came roaring in at nearly 1900 km/s, more than double the average. At this speed, it took less than 48 hours to reach Earth. That's considered extremely fast by solar standards, and it compresses Earth's magnetosphere far more violently. The shorter the travel time, the less time Earth has to prepare, and the more direct the hit becomes. Scientists use models like WSA-Enlil to forecast CME arrival. These simulations track plasma density, speed, and direction in 3D space. In this event, the model showed not just one shock front, but two stacked CMEs merging midway, amplifying the energy before impact. That stacking effect is what made this storm so intense. Earth was hit by compressed layers of high-energy particles, increasing radiation pressure and pushing magnetic thresholds beyond warning levels. Speed matters, and this one came like a solar bullet. What if this becomes a G5 extreme event? A level 5 or G5 geomagnetic storm is the highest on NOAA's space weather scale. It's rare and dangerous. While June's storm is currently at G4, scientists say it's on the edge of G5 threshold. If another CME follows, or if magnetic pressure builds further, we may cross into extreme territory. A G5 storm can cause widespread power outages, destroy satellite electronics, ground airplanes, and disrupt internet infrastructure. Fiber optic systems themselves are safe, but their powered nodes aren't. Routers, substations, and data relays could all fail if voltage spikes go unchecked. During the Halloween storms of 2003, the last major G5 event, 10 satellites malfunctioned, flights were grounded across the globe, and NASA lost contact with multiple probes. If the current solar behavior continues, June 2025 may become the first full G5 storm of the modern tech era. If that happens, we're looking at possible blackout zones, GPS chaos, communication breakdowns, and economic loss in billions. Government agencies are already rehearsing emergency protocols behind the scenes, because when the sun gets serious, there's no switch to turn it off. How solar flares differ from CMEs, and why both matter. Solar flares and coronal mass ejections often happen together, but they're not the same. A solar flare is a flash of light, a sudden burst of energy from the sun's surface. It travels at the speed of light and reaches Earth in just 8 minutes. Think of it like the flash before the punch. CMEs, on the other hand, are the actual punch. Giant blobs of plasma and magnetic fields thrown into space. They move slower, but carry more physical force. A flare can knock out radio instantly. A CME hits the magnetosphere and causes power surges, auroras, and geomagnetic chaos. Flares are categorized from A to X, with X being the strongest. CMEs don't use the same scale. They're measured by speed and density. Sometimes both come from the same sunspot, flare first, CME second. And when this happens, Earth gets hit with a 1-2 combo. Understanding the difference is critical. Some flares cause no CMEs, some CMEs are stealthy and arrive without flare warning. But when both align, like they did in June 2025, that's when we see storms strong enough to shake the entire planet's electromagnetic shield. Historical storms, what we learned from 1989 and 2003 events. In March 1989, a powerful solar storm caused a 9-hour blackout in Quebec. It was one of the first modern lessons that space weather could shut down a major city. Transformers melted, voltage collapsed, and over 6 million people were left without power, all from a CME. Fast forward to 2003, the infamous Halloween storms. This time, multiple X-class flares and CMEs hit Earth over a 2-week span. Air travel was disrupted, 10 satellites malfunctioned, and auroras were seen as far south as Texas and Rome. It was one of the most intense events in recorded space weather history. These events taught scientists the importance of real-time monitoring. After 2003, agencies began investing in space weather forecasting satellites like SDO and DSCOVR. Today's alerts, protocols, and international coordination owe their existence to the chaos of those earlier years. What's scary now is how similar 2025 is starting to look. From the magnetic instability to the timing of impacts, patterns are repeating. The difference? We're more digitally connected, and that makes us more vulnerable than ever before. Spiritual meaning and human energy. During solar events, throughout history, many spiritual traditions have linked solar storms with human consciousness shifts. During intense solar activity, people report vivid dreams, emotional swings, deep meditative states, and even unexplained awakenings. Is it coincidence, or is solar energy subtly affecting our bodies and minds? Scientists confirm that geomagnetic storms can influence brainwave patterns, circadian rhythms, and melatonin levels. Some people feel exhausted, anxious, or hypersensitive during solar storms. Others feel an inner fire, clarity, or an unshakable calm. It seems the solar storm doesn't just hit Earth, it echoes within us. Many spiritual teachers believe that solar events carry high-frequency energy that upgrades the human biofield. They say this energy removes emotional blockages, accelerates healing, or forces suppressed feelings to surface. That's why, during times like now, some people experience breakthroughs, and others emotional chaos. Whether you're spiritually aligned or not, solar storms remind us that we are not separate from space. We are influenced by celestial rhythms. The light hitting our planet is ancient. And in moments like this, it's not just the skies that glow, but human energy too.